Okay, in this example, astronauts on the first trip to Mars take along a pendulum that has a period on Earth of 1.5 seconds. The period on Mars turns out to be 2.45 seconds. And what is the free fall acceleration on Mars? Okay, so let's first draw a picture of our case. So we've got our pendulum. And we'll say this is the vertical. Here's our bob on the pendulum. This is our theta. And if we think about what's going on, we're going to break our components. We're going to look at our forces. And so we have a force of tension here, and that tension is in the radial direction. So I'm going to break up my components now into the radial direction and the tangential direction. So I've got the force of gravity. I've got this force of tension. And let me just move this to the other side. So this is my force of gravity. But if I want to break up the force of gravity into the radial component and a tangential component, I'm going to do something like this. Something like that, where this is my theta, same theta, because this theta here is between the vertical and this, the line, the string for my pendulum, and this theta down here is between the force of gravity and the extension of the string. And so this component right here is going to be Fg in the r direction, and this component is going to be Fg in the tangential direction. And when I think about the acceleration, the bob, or the little mass, is not moving in the r direction. The radius isn't getting bigger, but it's moving in the tangential direction. So it's moving, this is my tangential direction. So that's what it's how it's moving. So when I think about the free, my force model, right, my sum of the forces, I'm caring about the tangential direction. And that's where I'm going to have my acceleration, m times a. Now, looking at my picture, I can see that the tangential direction is opposite my angle, and so opposite over hypotenuse is my sine. So to get the tangential component, I'm going to write here Fg sine theta. So the sine is opposite, and that's why I'm picking Fg, the tangent component is opposite my angle, is equal to ma. Now I know Fg is mg, sine theta is equal to ma. So I can cancel out my m's. And I know I'm going to assume small angle approximation. Approx. And that's just telling me that sine theta is approximately equal to theta for really small angles, like less than a degree. So I'm going to plug that in. So g of theta is equal to a. And now I'm going to use the fact that I've got, if I think about a circle, and I'm going to draw it so that it makes sense for our case. Right? If this is like an arc of a circle, this is my s, this is my theta, and this is my r. So the s is really the tangential, has a tangential direction. So I'm going to plug in, so I know that s is equal to r theta. So therefore theta is equal to s over r. So I plug that in over here, g, and then s over, my r in our case is L, this length from here to here. That length is the length of my string, L. So that's what I'm going to plug in for my R, is equal to, now A is really the acceleration. And the acceleration is just the second derivative, d squared of s, because s is the tangential direction, over dt squared. Okay, and so just like we did for the spring, we now have, we now could substitute in, right? I know that my s is equal to some amplitude times cosine of omega t plus phi. And if we take the derivative, we get the velocity. If we take the derivative again, we get d squared s over dt squared is equal to a. And remember that we take the derivative first, we get sine, and then we have to take the derivative of what's inside, so we get an extra omega. And then when we take the derivative again of sine, we get cosine, and we get an extra omega. So I'm going to put that omega squared, and I get cosine of omega t plus phi. But that's actually equal to d squared s over dt squared is equal to a cosine omega t plus phi is just s. So I get omega squared s. And now I can go back and plug that in. Let's move this up a little bit. I can go back and plug that into this equation right here for d squared s over dt squared. So I'm going to say g over L times s is equal to omega squared s. And so we have s on both sides, so we can cancel them out. And we get omega is equal to the square root of g over L. So that's great and all, but what are we trying to find? Well, we should have done that right from the beginning, right? We should, let's do that now because I forgot, our givens. Let's do our givens first. Our given is that t on Earth is equal to 1.5 seconds. So the period of the pendulum on Earth is 1.5 seconds, and the period on Mars is equal to 2.45 seconds. And I'm trying to find the acceleration. So I'm trying to find g on Mars. Okay, so notice here, we don't know what the length is. They don't tell us what the length of the pendulum is, so we're going to need that. So what we can do is, we know the period on Earth. So what we're going to do is we're going to substitute we're going to plug in an equation for omega, and that equation for omega is 2 pi over the period is equal to g over L. Okay, so I know the period on Earth, and I know the gravitational, the strength of gravitation on Earth. So I'm going to solve for L here. So to solve for L, I'm just going to cross multiply. So 2 pi L is equal to g times capital T for period. And to get L alone, I'm just going to divide both sides by 2 pi. So I get g T. Oh, and I forgot to do something here. This should be squared. Right, so I'm going to have 2 pi squared here. And I'm going to have t squared here. And I'm going to have t squared here and divided by 2 pi squared. And when I plug my numbers in, which are going to be, let's see, 9.8 meters per second squared, times the period is 1.5 squared, divided by 2 pi squared. And when I plug that in, I get L is equal to 0.56 meters. Okay, so now I can use that and use the equation again to find G. So what I'm going to do is I'm going to use, let me plug in what I'm going to use first. I'm going to use this equation right here. So what I want to use is I want G, so I'm going to say G is equal to omega squared L, and G is equal to 2 pi over the period squared times L. And so that's the equation I'm going to use. Let me just move down. All right, so I'm going to bring that equation down. So I'm going to say G is equal to 2 pi over the period squared times L. And when I plug in my numbers, I'm going to get 2 pi. Now I need to plug in 2.45 for the period on Mars squared. And now I'm going to have 0.56, the length that I found in the last part. And I get G is equal to 3.67 meters per second squared on Mars, just from information about a pendulum.